FSDP Faculty Student Development Program. Today is the final session. We'll have after this session, we'll be having an post quiz. We'll be sending the mail to all the participants. In that link, we will be having an questions regarding the 3-day sessions. So you'll be answering the questions. Based on that, we'll be providing the certificate. Post quiz is compulsory to get an e-certificate. On the announcement, I now request Mr. Pati Lakshminarayan, PALS champion, to introduce the speaker.
Thank you, Kishore. I hope both the speakers have joined now, or they are immediately going to join. First of all, it is great to see such a response for this current technology trend series, which we are conducting for 3 days, including faculty as well as students. I definitely, this kind of a response will help us to arrange more such series in future. So I am very much glad. I am glad to introduce the speakers who are from BEL today. So let me introduce the first speaker, Dr. Saravanan. Dr. Saravanan is a distinguished electronics professional with over 25 years of experience in the field of professional electronics. He began his career in 2001, joining Bharat Electronics Limited as a member of the research staff at the Center Research Laboratory following the successful completion of his post-graduation from PSC College of Technology, Coimbatore. His research expertise spans a broad and impactful spectrum, including low-power embedded platform development, smart handheld devices, porting embedded operation system, and the design of system-on-chip architectures. He currently heads the SOC Design Center at the Product Development and Innovation Center, BEL, Bangalore. A testament to his technical expertise and vision in the current age electronics research. In 2025, Dr. Saravanan earned his doctorate from MS Ramaya University of Applied Sciences, with his research focused on the domain of OFDM, orthogonal frequency division multiplexing system. Throughout his illustrious career, he had been recognized with several prestigious accolades, including the Raksha Mandri's Award, BEL R&D Excellence Awards, and the BEL Key Contributor Award. He also holds 6 Indian patents to his credit, reflecting his significant and sustained contribution to innovation in electronics and embedded system. We are fortunate to have you, Dr. Saravanan. I welcome you. In this way, I want to introduce the next speaker also. The next speaker is Dr. Saravanan Karthik. Karthik is currently serving as a Deputy General Manager at the SOC Design Center, BEL, Bangalore, where he heads the physical design and analog RF portfolio. He has over 2 decades of experience in the design, development, and successful delivery of production proven full custom analog AICs, MMICs, and SOCs for strategic and mission-critical application. His expertise spans the complete semiconductor product lifecycle, with demonstrated experience in taking complex designs from specification through design, verification, physical implementation, tape out, and production. He has been granted 5 patents, published 15 IEEE papers, and is recipient of R&D awards. He completed his undergraduate students at RVCE and holds master degree from microelectronics from BITS, Milan. He is also a member of IEEE societies, including CACS, EPS, and SCCS. I welcome Dr. Karthik also for this session. Over to Dr. Saravanan. Over to you, Kishore.
Saravanan sir, can you share your screen and start the session?
Yeah. Thank you. Just hold on. Maybe another 10-20 seconds. Yeah, there is minor glitches there.
Sure, if you want to present PPT, you do that so that we can talk. Dr.
Sir, do you
Saravanan,
want
whether
me to
Kishore-
present the
Kishore can
PPT?
present it? Project the PPT?
Dear participants, please apologize for the unexpected glitch. Let us wait for a few more seconds. A speaker is setting things right. So please give us a few more minutes. By the meantime, can we have any faculty, at least any faculty, anybody is willing to summarize or share your opinions on the past two sessions, your feedback? Any faculty want to do that? Lot of students from Narayana, KIT and other colleges.
Sir, சொல்லுங்க sir.
No response. Narayana, Pratima, you want to summarize?
Can you? Yeah, is it okay? Are you getting it? Yeah.
Saravanan, sir?
Yes, sir. You have to hear us? I think Shikhar will be sharing the presentation.
Sarnan sir, can you see my screen?
Yeah, you can put it in full screen. Yeah, it's visible.
Okay, it's in a slideshow.
Sir, can we start?
Yes, you can, sir.
Yeah. Good afternoon to all. Thank you, Pati sir, for warm introduction. I also thank PAL for giving us this opportunity. Good afternoon to everyone. Over the next hour, we are going to take a comprehensive journey through one of the most strategically consequential subjects facing India today, our semiconductor future. I want to be clear from the outset, this is not a technical presentation about chip design. This is a strategic intelligence briefing about national power. Semiconductors are oil of 21st century, the resource that powers everything and the resource that determines who holds leverage over whom. We will cover 5 broad areas today. First, India's 70 history, what we tried, what we built, and what we lost. Second and third, the India semiconductor mission in its two phases. What has been committed, what has been achieved, and what remains to be done. Fourth, we will benchmark India against the major global players, the US, Europe, China, Japan, and Korea. Because we cannot understand our strategy without understanding theirs. And fifth, we will go deep on design sovereignty and national security. Because this is ultimately why all of us in this room should care about wafer fabs and photoresist. Let us start the presentation. Yeah, we can move to the next slide. We can move to the next slide. Before we can understand where India is going with its semiconductor mission, we need to understand where it has been. And the history is simultaneously inspiring and deeply sobering. India had genuine opportunity to become a semiconductor manufacturing power before Taiwan, before Korea, in some case before China. We did not take them. Understanding why is essential context for evaluating whether the current effort will succeed where previous ones failed. Section 1 covers the period from 1960 to 2020, 7 decades of aspiration, interruption, and missed opportunity. Next slide. Let me start with a story most people in this room probably don't know. In the 1960s, at the very dawn of silicon revolution, Fairchild Semiconductor, the company that invented the planar integrated circuit, the foundational technology of everything we call a chip today, evaluated India as a manufacturing location. They looked at our engineering talent, our low-cost labor, our government interest. And then they encountered India bureaucracy, licensing approvals, import restriction, land allocation delay, all has forced them to leave the country. They went to Malaysia instead, where they set up one of first offshore semiconductor assembly operation. That single movement set the template for the next 60 years. Now separately, Bharat Electronics Limited was doing genuinely impressive work. Founded in the year 1954, by 1962, it was manufacturing germanium transistor. By 1967, after a technology transfer from Philips, it was making silicon transistors of such a quality that companies would queue up to place orders. ITI was building the India telecom infrastructure. The demand was there, the talent was there. What was missing was a policy environment that could convert demand and talent into a manufacturing scale. The Fairchild story is not a short, interesting story. It is prophecy of pattern that would repeat itself for 6 decades. Next slide. Now we get to the most tragic story in Indian industry. Semiconductor Complex Limited, SCL, established in the year 1983. Think about what this means. India established a dedicated VLSI fabrication facility before. TSMC was founded, TSMC was established in 1987. SCL started in 1984 with a 5-micron CMOS process, the contemporary global standard, and it did not stay there. By the late 1980s, SCL has advanced to 800 nanometer technology, just 1 to 2 years behind Intel and Global Frontier. At that point, China had not entered the fab space. Taiwan was just getting started. India was actually ahead. And then, on the night of September 1989, a devastating fire tore through the SCL complex. The infrastructure was severely damaged. The response from government was slow, underfunded, and ultimately inadequate. The equipment was not replaced at the pace needed to keep up Moore's law. By the time SCL was partially operational again, the technology gap had begun to widen. Then, in 1991, the economic liberalization and chips from Taiwan and Korea flooded Indian market. SCL never recovered commercially. It was transferred to the Department of Space, where it produced low volume of chips for ISRO. By 2020, India was almost 12 generations behind the global frontier. In 1987, it was 2 years behind. The compounding of lost time in Moore's law industry is brutal, and we are still paying for that September 1989 incident. Next slide, please. The Indian government of 1984 to 1989 deserves credit for recognizing the strategic importance of electronics. The computer policy of 1984 was genuinely liberalizing. It relaxed licensing, reduced import duties on computers, and created the condition for India's IT boom. NASCOM was founded in 1988. The same year, CDAC was also established and produced the Param supercomputer. Several important institutions were created in this period. Seri in Pilani for semiconductor device research, Samir in Mumbai for microwave IC design, Gatak in Hyderabad for compound semiconductor. These were real investment with real capabilities. But here is a structural problem. The 1991 economic liberalization, which was necessary and beneficial in many ways, simultaneously destroyed the protected demand environment that could have sustained domestic semiconductor manufacturing. When cheap Taiwanese and Korean ICs became freely available, Indian fabs simply could not compete on price. And India's best engineering talent, instead of going into semiconductor manufacturing, went into software industry. Because these big software giants were paying better than the indigenous fab units. India built one of the world's deepest semiconductor design talent pool while completely abandoning semiconductor manufacturing facility. We created a design without fab. Paradox that defines our challenge to this day. Next slide, please. Between 2007 and 2020, India made 3 serious attempts to establish a semiconductor manufacturing ecosystem. All the 3 attempts failed, and it's worth understanding, especially why it failed, because the reasons are directly relevant to evaluating whether ISM 1.0 and 2.0 will succeed. The 2007 policy offered 20% capital subsidies and tax holiday. Sounds reasonable, but investors compared it to Malaysia, which was offering 30%, and China, which was offering land, electricity, water, and tax exemption simultaneously. And they choose Malaysia and China. The 2012 cabinet approval was more serious. 39,000 crores committed for 2 fabs. The Gujarat government offered 300 acres of land. A credible bidder, JP Associates, with IBM was selected. And then the private capital side collapsed. The government commitment was there. The private sector execution was not there. Most damningly, a multinational semiconductor company was in process of relocating a fab to India during this period. It watched the JP Associate experience and concluded that India could not execute, and ultimately they moved to China. China gave them everything they needed. India lost the facility and 4,000 job opportunities and the confidence of the global semiconductor investment community. The 2015 ESDM program, Electronic System Design and Manufacturing program, attract some assembly and testing investment, but no fabrication. The COVID-19 pandemic and the semiconductor shortage of 2020 to 2021 was event that finally created the political will and the policy ambition for ISM 1.0. Every one of those failed attempts is a lesson that ISM must apply. Next slide, please. While the commercial semiconductor ecosystem was failing, India's defense establishment was quietly building a parallel, isolated, and fundamentally constrained semiconductor capability. GATEC in Hyderabad manufactures gallium arsenide MMICs for radar and electronic warfare application. Sitar in Bangalore provides real-estate design service for DRDO laboratories. Stark handles semiconductor assembly and packaging for strategic application. These facilities are genuinely capable in their domain, but they have 2 fundamental limitations. First, they are used only for defense, no commercial volume, which means no scale economies, which means perpetually expensive and perpetually 1 or 2 generations behind the commercial frontier. Second, they cannot manufacture digital logic at modern nodes. India's defense system uses chips fabricated at foreign fabs, primarily in Taiwan and Korea. A senior scientist said it plainly, once we send the chips out for fabrication, we have to share our design. It no longer remains our IP. The security risk is always there. That code should be on the wall of every strategic planning office in India. We'll move to the next slide. I want to pause and look at this timeline holistically because the pattern it reveals is more important than any individual event. In 1956, it's 1954, Bell was established. In 1984, SEL started the activity the same year as Mac, 1 year after the IBM PC. In 1987, India is 2 years behind the global frontier. By 2022, it is 12 generations behind. That is the cost of 35 years of policy inconsistency. The lesson boxes on this slide captures the 4 structural reasons for the failure. The lost lead. We had it, we lost it. The design paradox. World-class designers, genome manufacturing facility. The ecosystem gap. Unlike Taiwan or Korea, which started with assembly and worked up, India tried to start at the top and failed. And the policy credibility problem. 3 policies in 15 years, 0 fabs. ISM must break all 4 patterns simultaneously. The encouraging thing is that the current approach with the anchor tenants, credible fiscal support, and infrastructure pre-committed is structurally different from all previous attempts. The discouraging thing is that execution has always been India's deficit, not ambition. We'll move to the next. We now move to the present. December 2021 was a genuine turning point in Indian semiconductor industry, not because the cabinet approved a program, but because for the first time, the program was designed at a scale and with a credibility that actually attracted the global semiconductor investment community. Section 2 covers ISM 1.0, what was designed, what was approved, what has been built, and what the honest assessment of achievement and gaps looks like. We'll move to the next slide. The numbers on this slide tells the story. Rupees 76,000 crore in fiscal incentive, up to 50% capital support for Silicon Fab. 10 projects approved. Rupees 1.6 lakh crore in total private investment committed across 6 states. These are real commitments, not expression of interest. Tata Electronics, partnering with PSMC of Taiwan, is building a 28 nanometer fab at Dholera, Gujarat. ASM lithographic equipments are getting installed. First, silicon is targeted for late 2026. Micron Technology, one of the world's 3 DRAM manufacturers, committed $2.75 billion for an advanced packaging and testing facility at Sanad, Gujarat. That Micron investment is critically important, not for what it produces, but for what it signals. When a Tier 1 US semiconductor company puts nearly $3 billion into India, it changes the global investor community risk perception of India as a semiconductor destination. Carnegie India's assessment, reference on this slide, makes exactly this point. The credibility signal of ISM 1.0 is its most important achievement. The program also includes the design-linked incentive scheme, the Chip to Startup program, connecting 111 universities to chip design tools, and the Digital India RISC-V program. The foundation has been laid. The question is whether ISM 2.0 can build the structure. Yeah, move to the next slide. Yeah, this slide gets to the heart of India's semiconductor paradox. India has approximately million VLSI engineers. Virtually every major semiconductor company in the world has a design center in India. Qualcomm, Intel, AMD, Texas Instruments, you name it. All have significant Indian design operations. Chips designed in India are powering devices around the world. But every one of those chips once designed is sent to TSMC in Taiwan, or Samsung in Korea, or SMIC in China for fabrication. India has the brain, rest of the world has the body. The design linked incentive scheme is the policy mechanism to convert India's design excellence into a Indian IP ownership. It reimburses up to 50% of qualifying design infrastructure costs, EDA tool licenses, tape out costs, prototyping. The Dhruv 64 processor and the Saxi processor series, both based on RISC-V architecture, are the flagship indigenous design. In August 2025, Honorable Prime Minister announced that India's first fully indigenous chip, designed in India, fabricated in India at SCL using RISC-V architecture. That is a symbolic milestone, but symbols matter. For the first time, an Indian chip will be designed and fabricated within Indian border under Indian IP. Yeah, we'll move to the next slide. If you want to understand why India failed at semiconductor 3 times before ISM 1.0 and why there is a cautious optimism that ISM may be different, look at this slide. The root cause of SCL failure was not the fire. The fire was the triggering event. The root cause was that the promised infrastructure, subsidized electricity, reliable water, vibration-free environment was never delivered. Metcom Silicon, the IISc Bell joint venture, polysilicon joint venture in the 1980s collapsed because the electricity subsidy never arrived. An attempt to grow silicon at BHEL in the 1990s failed because a railway track ran next to the facility and the vibration made precision crystal growth impossible. These are not edge cases. They are the systemic reality of building precision manufacturing in India infrastructure environment of that era. ISM 1.0 is different because it identified specific locations. For example, Dholera Special Investment Region in Gujarat, where infrastructure was pre-built and committed before investors were invited. The Press Information Bureau's India Semiconductor Revolution article makes the point that 3 changes make ISM viable today that did not exist before. India's digital payment ecosystem creating data infrastructure demand, Make in India creating electronic manufacturing depth, and the PLI scheme creating an electronic supply chain that can support semiconductor investment. The infrastructure questions has not been fully answered, but for the first time, it has been seriously addressed. Yeah, we can go to the next slide. Let me be honest about this assessment because strategic planning requires clear-eyed evaluation, not cheerleading. On the achievement side, rupees 1.6 lakh crore is committed, investment is real. Micron's facility is under construction. Tata's Dolera Fab is under construction. The DLI scheme has seeded 50 plus fabless startups. SCL has fabricated its first DLI student chip. These are genuine first of its kind achievement. On the gap side, the 10 approved projects are all at 28 nanometer and above. The global frontier is at 2 nanometer. India has attracted packaging and assembly investment and one logic fab. But the compound semiconductor supply chain, the equipment ecosystem, the domestic EDA tools, none of this exists at meaningful scale. Carnegie India's conclusion is that right framing. ISM 1.0's most important achievement is the credibility signal, not the output. India proved it can attract global semiconductor investment. ISM 2.0 must now use that credibility to actually build the semiconductor sovereignty, indigenous IP, domestic logic fabrication at advanced nodes, the trusted supply chains and certified fabs. The credibility foundation has been built, the house has not yet been constructed. We'll go to section 3. Yeah, next. ISM 2.0 is where India's semiconductor ambition becomes genuinely global in scale. The approval of 1,27,500 crore, nearly double that of ISM 1.0, signals that India is not treating this as an experiment. It is a sustained multi-decade national commitment. Section 3 covers the architecture of ISM 2.0, its 6 pillars, the advanced node roadmap, the RISC-V and indigenous IP agenda, and what success looks like by 2035. Let's move to the next slide. The 6 pillars of ISM 2.0 represent a qualitative shift from ISM 1.0. ISM 1.0 was about getting the ecosystem started, attracting anchor investment, establishing fab and packaging facility. ISM 2.0 is about consolidation and advancement, pushing towards leading edge nodes, building domestic IP, and crucially, addressing the supply chain gap that ISM 1.0 left unresolved. Pillar 1 targets the advanced node roadmap, 7 nanometer by 2030, 3 nanometer by 2033, 2 nanometer by 2035. These are ambitious, but the ISM 2.0 framework provides specific financial incentives for node transitions, not just facility construction. Pillar 4, equipment and materials. With 40,000 crore dedicated to it, perhaps the most strategically significant new addition. India cannot have a sovereign semiconductor industry if every chemical, every process gas, every piece of lithographic equipment is imported. This pillar is the acknowledgement of that reality. Pillar 6, trusted and secure manufacturing, is one of that matters most for everyone in defense. For the first time, India is formally designating a category of semiconductor manufacturing that is security certified with provenance tracked supply chain for defense and strategic application. This is the Indian equivalent of the US Department of Defense Trusted Foundry Program. It has taken India 20 years longer than the US to establish this framework, but it is now in policy. Yeah, we'll move to the next slide. Sure. If we put the advanced node roadmap in perspective, TSMC today is manufacturing at 2 nanometer, Samsung is at 2 nanometer, Intel is at approximately 2 nanometer with its 18 Armstrong process. India's first commercial silicon fab, Tata Dolera, is targeting 28 nanometer. That is 12 generation gap for the current frontier. ISM 2.0's roadmap targets closing that gap to approximately 4th generation by 2035. 2 nanometer India versus 1 nanometer are below 40 SMC. That is still a gap, but it is a strategically manageable gap, and particularly for defense application where performance per watt and reliability matter more than absolute leading edge status. The technical pathway from 28 nanometer to 2 nanometer requires at some point a transition from FinFET to gate-all-around architecture. ISM 2.0's India's Semiconductor Research Center program is investing in exactly this gate-all-around transistor process development at IIT level, building the research capability that will feed into future fab generation. Niti Aayog's assessment identifies India's unique advantage clearly. The engineering talent to execute this roadmap exists in India. The market demand to justify the investment exists in India. What has been missing in the sustained policy commitment? ISM 2.0 represents the commitment at the required scale. Move to the next. This slide covers what I consider the most underappreciated strategic dimension of ISM 2.0. We talk a lot about fabs, about nodes, about investments. We talk much less about instruction set architecture, ISA, the most fundamental layer of computing. Every computer executes instruction definitely by its ISA. The two dominant ISA in the world are ARM, owned by ARM Holding, a company that is UK originated, Japanese controlled SoftBank, and now partially listed on NASDAQ, and x86 architecture controlled by Intel and AMD, both US companies. Both are subject to US export law. Both are subject to the export control decision of their home government. If the United States government decided tomorrow to restrict the export of ARM or x86 license to India, a scenario that is extremely unlikely, but not theoretically impossible. India's entire government and defense computing infrastructure would be in legal jeopardy. RISC-V eliminates this risk entirely. It is an open specification governed by RISC-V International with no single controlling authority and no export license requirement. India's Shakti processor developed at IIT Madras and Dhruv 64 server processor are India's RISC-V base. The Digital India RISC-V program mandates government procurement preferences for RISC-V design. This is a ISA sovereignty, layer 1 of design sovereignty stack, and it is the necessary foundation for everything that follows. Next slide, please. The market number on the slides are not aspirational projection invented by a government committee. They are based on India's actual electronic demand trajectory. The semiconductor market grew from $38 billion in 2023 to $45 to $50 billion in 2024 to 25. The 100 to 110 billion target for 2030 is anchored in India's 5G rollout driving handset replacement, the EV transition driving automotive chip demand, AI infrastructure investment, and the defense modernization program. What matters strategically is that this demand is large enough to justify domestic manufacturing. TSMC's Arizona fab needed US government support partially because US domestic demand alone was insufficient to justify the economics at the required scale. India's domestic demand by 2030 will be large enough to justify significant domestic fab capacity on commercial grounds alone. A qualitative difference from the 1980, when SCL was producing for a tiny domestic market that could not sustain commercial scale economics. Press Information Bureau's framing of this as civilizational transition is ambiguous language, but it captures something real. India is making the transition from technology consumer to technology creator, and the semiconductor mission is the centerpiece of that transition. The geopolitical movement, China plus one sourcing strategies, allied trust, supply chain preferences, amplifies the commercial case significantly. Yeah, we'll move to the next. This is a slide that most people who talk about India's semiconductor mission skip over, and it is arguably the most important one. A semiconductor fab is only as sovereign as its supply chain. If you build a domestic fab but import 100% of your photoresist from Japan, 100% of your process gas from a multinational supply chain, and 100% of your lithography equipment from ASML in Netherlands, you have a domestic fab with a foreign supply chain. And this is not sovereignty. The October 2022 US export control on semiconductor equipment to China were the definitive demonstration that equipment supply is a geopolitical weapon. China is the world's second largest semiconductor manufacturer, and it was effectively cut off from the most advanced manufacturing tools by a policy decision in Washington. India makes note of it. The ISM 2.0 equipment and material sub-scheme of rupees 40,000 crore is the acknowledgement of this reality. It won't make India self-sufficient in extreme ultraviolet lithographic equipment. Nobody except ASML. Even ASML has 5,000 supplies across 40 countries, but it can build domestic capability in less critical equipment, in, in specialty chemicals, in process gases, in wafer handling, reducing the number of single source foreign dependencies. And the National Critical Mineral Mission, with rupees 7,280 crore for rare earth materials, is critically linked because China controls 80% of global gallium and 60% of germanium, both essential for compound semiconductor that Indian defense electronics require. Yeah, we'll move to the next. I want to be precise about what changed between ISM 1.0 and ISM 2.0 because if you blur this distinction, you miss the strategic significance of the evolution. ISM 1.0 asks, can we attract global semiconductor investment to India? The answer we have seen is yes. ISM 2.0 asks a harder question, can we build a complete domestically anchored semiconductor ecosystem that is not just for investment posted in India, but genuinely sovereign? The shift from 28 nanometer to 2 nanometer in the node roadmap is the most visible difference. But the more important differences are in the areas that were absent from ISM 1.0, the equipment and material sub-scheme, the explicit trusted foundry designation for defense, the DLI 2.0 emphasis on IP retention in India rather than just IP development in India, and the 200 colleges and 1 lakh engineers per year talent pipeline. ISM 2.0 is not just a bigger ISM 1.0, it is qualitative different ambition, from participation to ownership, from assembly to logic fabrication, from foreign IP manufactured in India to Indian IP manufactured in India. Whether execution matches ambition is a central strategic question for the next decade. Yeah, we'll move to the next. To evaluate India's semiconductor strategy intelligently, we need to understand what every other major power is doing simultaneously. The global semiconductor policy landscape of 2021 to 2026 is unprecedented. $500 billion or more in government investment across the major economies, all motivated by the same recognition that semiconductor dependency is the strategic vulnerability. Section 4 looks at each major player, the US, Europe, China, Japan, and Korea. What they are investing, what their strategic logic is, and what India can learn from each approaches. Yeah, we'll move to the next slide. The structural shift captured in the top part of the slide is the essential context for everything that follows. Before 2020, semiconductor policy was largely left to the market. The assumption was that comparative advantage, global supply chain, and commercial efficiency would produce optimal outcomes. COVID-19 destroyed that assumption. The automotive sector alone lost production of 4 million vehicles globally due to chip shortage. The German government estimated it lost to 1 to 1.5% of its GDP in 2021, roughly translates to 40 billion euros from semiconductor supply disruptions. And then the Taiwan risk calculation was publicly articulated by senior US officials. Bloomberg Economics estimated that a Taiwan state conflict could cost the globally $10 trillion because 90% of leading edge chips are manufactured in one small island, the China claims as its territory. At that point, semiconductor policy became national security policy everywhere simultaneously. The comparison table on this slide shows the scale of coordinated global action. $52.7 billion from the US, 43 billion euro from Europe, 47 billion dollars from China's Big One Phase 3, and 11.546 billion dollars from Japan Rapidus program, 450 billion dollars from Korea's private sector led strategy. India's combined ISM 1.0 and 2.0 commitment of approximately 2 lakh crore places in this league, which is the current positioning. Yeah, move to the next slide, please. The US chip national semiconductor program are measured. $52.7 billion in direct funding, $24 billion in investment tax credit. The investment it has triggered are staggering. TSMC is putting $40 billion into Arizona. Intel is investing 20 billion plus in its 18 Armstrong process node. Samsung is building a 17 billion fab in Taylor, Texas by 2025, the CHIP Act has reached and received 670 expression of interest from semiconductor companies and was projected to generate 93,000 construction jobs and 43,000 permanent semiconductor manufacturing positions. The US approach to export control is equally important. The October 2022 BIS rule restricting semiconductor equipment to China, including ASML's most advanced deep ultraviolet machines, fundamentally changed the geopolitical landscape of semiconductor technology. The US demonstrated that it can weaponize the technology access, and it demonstrated this against the world's second largest economy. Every nation in the world, including India, took note. The lesson for India is clear. Frame semiconductor investment as national security spending, not industrial policy. The CHIPS Act is a security law that happens to create industrial outcomes, not an industrial policy that happens to have security benefit. India ISM would benefit from the same framing explicitly in legislation. We'll move to the next. Europe's approach is both instructive and cautionary. The 43 billion euro EU Chip Act of September 2023 has the right strategic logic. Reduce dependency on Asian chip supply, build European semiconductor sovereignty. But the European Court of Auditors 2025 assessment found that the headline target of 20% global market share by 2030 is unlikely to be achieved within the intended time frame. Why? Partially because the direct government funding component is modest relative to the expected private co-investment, and the private sector has been slower to commit than anticipated, and partially because building a semiconductor capacity in Europe faces the same challenge India faces. The ecosystem depth is missing. TSMC, Dresden facility, and Intel's Magdeburg commitment are genuine anchors. But the supply chain, the trained workforce, the chemical and equipment ecosystem, these take time to build. Europe's automotive chip dependency is a strategic driver. Every modern vehicle uses 1,000 to 3,000 chips, and EV vehicles uses 3,000 to 4,000 chips. Europe's automotive industry cannot afford to be chip dependent in a world where chip supply is geopolitical variable. The lesson for India: financial incentives alone are necessary but insufficient. Ecosystem depth, material, equipment, trained workforce, trained infrastructure must be built simultaneously with fab capacity. Yeah, we'll move to the next. China's semiconductor strategy deserves careful attention because it is the primary adversarial driver for both the US Chip Act and India's ISM. China has invested over $150 billion in semiconductors since 2014. Big Fund Phase 3 launched in May 2024 added another $47.5 billion, specifically targeted at overcoming US export controls on equipment and EDA tools. The most remarkable achievement of China's strategy from a technical standpoint is SMIC's 7 nanometer equivalent chip using multiple DUV lithographic exposure. A workaround for the fact that ASML EUV machines are denied to China. The Huawei Kirin 9000S processor manufactured by SMIC at the 7 nanometer equivalent node powered the Mate 60 Pro smartphone released in year 2023 and shocked the Western intelligence analysts who had assumed export control had capped China at 14 nanometer. This has three implications for India. First, China's military semiconductor capabilities advancing despite export control. Its defense AI chip, radar signal processor, and missile guidance system are manufactured at SMIC. Second, China controls 80% of global gallium and 60% of germanium material, the raw material for compound semiconductors that India needs for its GaN-based radar and EW systems. Third, China's aggressive self-sufficiency means India's primary strategic adversary will have semiconductor sovereignty before India does, unless ISM 2.2 accelerates significantly. We'll move next. Two very different models, both worth studying carefully. Japan is making the most audacious single bet in global semiconductor policy. Rapidus Corporation targeting 2 nanometer logic chips in mass production by 2027. That is faster than any advanced node fab has ever been built. Japan's reasoning is that it once had 50% of the global semiconductor market in 1988 before it lost to Taiwan, Korea, and the US. And Rapidus is the attempt to regain leading edge capability in less than a decade. The IBM partnership for 2 nanometer process technology and the IMAC collaboration for research and Hokkaido location with geothermal power and seismic stability all suggest serious technical planning behind the ambition. Japan's other semiconductor assert it even more powerful, its material and equipment supply chain. Japanese companies supply 90% of world's photoresist, a dominant share of silicon wafers, and critical etch and deposition equipment. Japan's strategy is choke point plus capability. It already controls key supply chain nodes and is adding a leading edge manufacturing capability. India's lesson from Japan: identify and develop one or two supply chain choke points, not just fab capacity. Korea's model is different. The private sector led at a scale that is breathtaking. Samsung and SK Hynix together are investing $450 billion in semiconductor capacity. Korea's approach is commercial leadership maintained by a private sector with government as enabler rather than direct investor. The talent pipe, KAIST, Seoul National University, is deeply embedded in the industry. India's ambition to produce 1 lakh VLSI engineers per year by 2030 mirror this model but needs acceleration. We'll go to the next slide. Next slide, please. This table is the strategic synthesis of section 4. I want to draw your attention to the rightmost column, India's relevance, because each row contains a direct implication for India's semiconductor strategy. The US export control leverage means India should position itself as the trusted alternative supplier for allied defense program, a status that requires the trusted foundry framework. Europe struggled to achieve its 20% target despite 43 billion euro in commitments. Wants India that money alone does not build an ecosystem. China's gallium and germanium control is an active supply chain risk for India's compound semiconductor program. Japan's choke point strategically suggests India should identify whether it has a natural supply chain advantage, rare earths, certain chemicals that it can develop into strategic leverage. And Korea's talent model is the template for India's engineering educational investment. The Arati Prabhakar quote at the bottom of this slide, all leading edge chips critical to US infrastructure, AI, and national security are being built in one fragile part of the world, is the most concise statement of why every nation in this comparison is acting simultaneously with urgency. Let us move to the next slide. We now reach the section that I consider the most important of this entire presentation, and the section most likely to be underappreciated in conventional semiconductor policy discussions. Design sovereignty and national security. When we talk about semiconductors and defense, most people focus on supply chain resilience. Can we get chips when we need them? That is important. But there is a deeper and more dangerous vulnerability. These chips you already have, the chips embedded in your weapon system right now may not be doing what you think they are doing. Hardware trojans, IP theft, fabrication level compromise. These are not hypothetical threats, they are documented realities, and India defense establishment need to understand them clearly. Let's move to slide, next slide. Design sovereignty is not a single achievement. It is a stack of 5 interlocking layers, and you need all 5 to be genuinely sovereign. Let me walk through each layer. Layer 1 is ISS sovereignty. Thus, India controls the instruction set that it computes and executes. Currently, no. ARM and x86 are foreign controlled. RISC-V is a solution. In layer 2 is ECDS sovereignty. Does India control the software tool used to design the chip? Current answer is no. Synopsys, Cadence, Mentor are all US companies subject to US export law. The 2022 control restricted the Chinese access to these tools. India is vulnerable to the same restriction. Layer 3 is IP core sovereignty. Do the functional building block embedded in India chip design belongs to India? Currently, no. ARM processor core, USB controller, memory interfaces, most are licensed from the foreign IP vendors. Layer 4 is fabrication sovereignty. Can India manufacture chip in domestically controlled facility? Currently, no. Though ISM is building towards this, Layer 5 is supply chain sovereignty. Are the materials and equipment for the fabrication sourced from non-adversarial diverse supply chain? Currently, no. The critical insight from this framework is that you can invest $1 billion in a domestic fab. Layer 4 and still be strategically vulnerable if layer 1, 2, 3, and 5 are controlled by foreign entities. India's semiconductor strategy must address all 5 layers simultaneously. Yeah, we'll move to the next. I want to spend a few minutes on hardware trojans because this is a threat that most defense planners are least well informed. And it may be the most severe latent vulnerability in any defense electronics. A hardware trojan is an intentional, malicious modification of an integrated circuit. Unlike software malware, it cannot be patched. Unlike a cyber attack, it does not traverse a network. It is baked into silicon at fabrication. Permanent, invisible to normal testing, and activated only under specific conditions designed to avoid detection during quality assurance. The 2007 Syrian incident is the most dramatic documented case. Israeli jets destroyed a nuclear installation in Syria while Syrian radar was allegedly rendered non-functional, reportedly because a remote kill switch was embedded in the commercial microprocessor running the Syrian air defense network. The 2012 Cambridge research on a military-grade FPGA, a military-grade device, found a publicly undisclosed hardware backdoor that allowed extraction of secret keys and full chip reconfiguration. These chips were used in US military system. The 2025 CloudSec research demonstrated that AI-assisted chips design introduces new hardware trojan risk because AI synthesis tool can embed malicious logic that is invisible to human review. The bottom line, any chip fabricated in a potentially adversarial nation or in a nation where adversarial intelligence services have access to fair process is a potential hardware Trojan vector. For India, this means chips fabricated in Taiwan, where Chinese intelligence services are documented to have an active collection operation targeting semiconductor companies, carry a non-zero hardware security risk. Yeah, we'll move to next. Yeah, we'll move to next. The United States addressed this problem in 2024 with DoD Trusted Foundry Program. The concept is straightforward. Identify a set of semiconductor fabrication facility that meet defense grade security requirement, domestic ownership or allied ownership with appropriate agreement, security cleared personnel, physical security, supply chain provenance tracking, and unmandated that classified and sensitive defensive designs are only fabricated at these certified facilities. The results over 20 years have been significant. US defense systems have progressively migrated to trusted foundry chips, eliminating the hardware Trojan risk at fabrication level and keeping design IPs under US legal jurisdiction. The CHIPS Act reinforced this, allocating $2 million specifically for secure and trusted domestic supply for the defense and intelligence community, the highest priority trench of entire program. India's ISM 2.0 Pillar 6 establishes for the first time the framework for an Indian equivalent. This is critically important, but creating a framework is only the beginning. Certifying a facility, establishing a security protocol, the personnel vetting, the supply chain provenance tracking, the physical security standards take 5 to 10 years of institutional development. If India starts now in 2026, a credible trusted foundry capability could be operational by 2031 to 2032. Every year of delay adds directly to India's semiconductor vulnerability window. Yeah. Yeah, we'll move to the next. Yeah, next. This presentation draws on 3 authoritative Indian sources on semiconductor question. And I want to synthesize their key arguments explicitly. Carnegie India story so far contributes 3 critical insights. ISM 1.0 is credibly different from previous failed policies because of scale, credibility, and anchor tenants. The Micron investment changed the global risk perception of India. And the most important lessons going forward is that you need the entire supply ecosystem, not just the anchor tenant. Niti Ayog's Future of India's Semiconductor Industry article contributes the strategic framework. Design sovereignty precedes manufacturing sovereignty. Without domestic IP, domestic fabs have no indigenously owned product to manufacture. India's 3 comparative advantages are engineering talent, democratic trusted partner status, and large domestic market demand pool. And the warning, a domestic fab that imports 100% of its input is not a sovereign facility. Press Information Bureau's India's Semiconductor Revolution contributes this civilizational framing. India is making the transition from technology consumer to technology creator. And this is not merely an industrial policy, but a national sovereignty projected analogous in scale to the 1970 indigenization of defense. Yeah, next slide, please. Yeah. Please, just go back. Go back. Let me summarize the strategic case in 7 propositions and ask you to consider each one seriously. 1, technology dependency is a strategic vulnerability and supply can be disrupted by conflict. Natural disaster or political decisions. Regardless of diplomatic relationships. 2, hardware Trojans are a real, documented, and currently unmitigated threat to India's defense electronics. 3, design without fabrication is half sovereignty. India's world-class designers are creating IP that leaves India's border every time a design goes to a foreign fab. 4. ISM 1.0 changed the game by establishing credibility. ISM 2.0 must win the game by establishing sovereignty. 5. Geopolitical window, China plus one strategy, allied trust supplier chains, US-China semiconductor decoupling that makes India an attractive partner will not remain open indefinitely. Every year of delay reduces the dividend. 6. RISC 5 is not an academic exercise, but the foundation layer of India's architectural independence. And Shakti and Dhruv 64 are national security infrastructure for India's computing sovereignty. 7. BEL is the integrating institution that bridges design excellence, manufacturing ambition, and different application. Yeah, next slide, please. Next slide, please. Let us close with the historical arc. In 1987, India was 2 years behind the global semiconductor frontier. By 2022, it was 12 generations behind. In 2026, with ISM 2.0 approved and the first silicon being fabricated at Tata Jolera, India is building the infrastructure to close that gap within a decade. Whether it succeeds will determine India's strategic autonomy for the rest of 21st century. The historic lesson is clear. India had the opportunity and lost it through policy inconsistency and infrastructure failure. What ISM 2.0 must prove it can sustain. The global context is unambiguous. Every major power is acting because every major power has recognized that semiconductor dependency is strategic dependency. India's democratic trusted partner positioning in a world where alternatives to Chinese chip supply are actively sought by US and allied defense procurement. It is geopolitical asset that may not last if India delays. And the design sovereignty imperative is not a future problem. It is the present reality of every Indian defense system that uses a foreign fabricated chip in potentially adversely compromised supply chain. The strategic planning function, whether at BEL or at ISM, exists precisely to build the order book and the capability of 2030 today, not to manage the order book of 2026. That is the mandate. The window is open. It is time to act now. Yeah, we'll go to next. Yeah, thank you. Yeah, go to the next slide, please. Thank you for your time and attention over this hour. The reference site on this slide represents the primary source for this presentation. I will close with a quote at the bottom of the slide, which I believe captures the essential truth of what we have discussed today. The silicon chip is the oil of 21st century, and the nation that refines it will power the next century of human progress. India has the talent, the market, the policy, and increasingly the investment. What it needs now is execution at rapidest level urgency, with chip level institutional seriousness, and with sustained political commitment that the strategic stakes demand. Thank you. Thank you all.
Thank you for the wonderful session, sir. Now Karthik sir is going to take this session, right, sir?
Yeah, he's ready.
Okay.
Yeah,
You
any
want me
questions?
to share screen? Okay, we'll go on the Q&A session at the end of the session, sir.
Oh,
Karthik sir, you're going to share the screen?
yeah, sure. Good to go. Can you please share the presentation?
Okay, wait a minute. Just a minute. Okay. You can start.
Can we start?
Yes, yes.
Okay, Kishore. Good afternoon, all. Thanks, Dr. Saravanan, for taking us through India's journey from the 70s, 60s to till date and where we are going to go forward and where we are looking at. So I will continue that with one of the most important building blocks of semiconductor industry, that's the transistor. The transistor has different avatars, but we'll focus on BJT, MOSFET, FinFET, and gate-all-around version of it because this has driven and this single element alone has changed the entire industry, and it has given, you can say, this is the mother technology, for almost all of the various technologies which have right now, ruling the roost. So the idea behind this presentation is that, the audience understands, I believe, you would have had all these, uh, equations and device architectures in your textbooks. But what we are trying to go through this particular lecture would be to understand the device architecture in an intuitive way and see where exactly the performance figure of merits needed some evolution. And then what was the cost for it, actually what we paid, what the industry paid, and where we are right now and how it will go through. It's a sort of, a retro look, and also where the things are moving towards, so that once we understand this in whichever domain in semiconductor industry you people tend to travel in future, be it on the ASIC side or the device physics side or the process side or the EDA side, and this understanding will really really help you out. And the key takeaway would be, like, once you get an idea about this particular what we are trying to say, then when you go back and back it up with a set of theoretical fundamentals, I think you will be set to explore the wonderful world of semiconductors. So let's start. So what the way we will go about with this is, first we will see, we are not going to get into deep into equations. We will be going through structural changes, what impact it had on electrical and process level changes. So that's how we will go ahead. These will be the three main things. Yeah, we'll go to the next slide, Kishore. Kishore, next slide, please. So yeah, the agenda I had already briefed. So first we'll understand why the devices evolve. And there are three main eras, if you can say: the BJT era, the CMOS era, the FinFET, and now the gate-all-around. So this will be the basic agenda. Next slide, please. Can we go to the next slide, Kishore? So before we get into it, usually I bring my references in the beginning itself so that it sort of, doesn't lose the importance. So there are many references available for the semiconductor devices and architectures. But I would, request the audience to go through the two main papers, Moore, the original paper of Moore, from where the Moore's law has evolved. That, if you see, it is really, you can read it during your study time. You can see that Moore has predicted, right up to the wearables, the electronic watches, what we wear. So there is a lot of insight into that paper, and it is pretty much, it can be understood by anybody. And then the Dennard scaling, it sort of gives you a view how the planar transistors evolved. And on the textbook side, Zay, as you all know, is the Bible for these physics of semiconductor devices. You can go through about the physics, how the physics dominates the transistors part of it. And there is a free IRDS IEEE.org. You can refer to this at any point in time, and most of the information from the industry is actually loaded onto it. And this is free, and it does not require any IEEE subscription or something like that. Apart from that, there are other useful things which have references which are put it into the slide. You can take a look at it later. Can we go to the next slide? So let's start the journey. So on the left side, you are seeing a point contact transistor. You would have seen this, in multiple slides. I'm also starting it with this. So what exactly there is a germanium bar with two gold contacts on either sides. So this happened in Bell Labs,
and people tried to, bias this germanium block and see how the current is getting amplified. Now, from that, if you see what I have traced here towards from 2024 onwards itself is a major block. This is only the FinFET journey. And this, again, the reference is from IRDS. So you can see from 2024 to wherever we are right now, we have already grown 3 generations. Thanks to AI, these are all getting, accelerated in a very, very exponential manner. So the key takeaway from this slide would be to basically understand how much we have grown in terms of device technology. So when you're thinking of device, think of it in the form of an architecture, device architecture. What are the components which are getting into making the transistor itself? What are the process? That itself is a big domain. And I believe for some of you, it might even explore, open up your careers for it. So can we go to the next slide, please? So why does a transistor change? I mean, transistor doesn't wake up in the morning and say, let me change. So it's like basically there are 3 or 4 major requirements why the transistor shape changes. And the main thing what we see is the economic pressure. So you have to have the market up and running with the latest technology products. So which means that you need more performance, more graphics, and more functionality. So which means that you need to pack in a lot of transistors. So this is the main driver. Now, in pursuit of the money, we try to, optimize the device architecture, but then there are physical limits. We hit the physical limits. And now, recently, with all the advent of data centers and other accelerator architectures which have come in, the thermal budget is a very big driver. It is talked to the extent where, a data center coming up can actually dry out the entire water table. So people have talked about the computing wall, memory wall. Now it is the power wall. So thermal budget is very, very critical. So these are some of the key drivers which actually drive the transistor evolution. So as I said in the beginning of this, so let us think through the entire lecture. We take it like a structure changes. Then once the structure changes, how the electrostatic control, basically how the current is controlled from the current flow across the channel is controlled. Then what are the processes actually in a fab which are required to build these evolving transistors? And at the end of the day, how it impacts the performance, power, and area. Of course, throughout this lecture, you may not understand the whole thing, but the idea is what we expect you to take home and then build it across during your career if you plan to take your career down the line of semiconductors. So as I mentioned, it's a structure. When I say the structure, in a transistor specifically, we are talking about how the gate sits and how many sides it controls. And on the electrical side, we are looking at subthreshold swing, drain-induced barrier leakage, ion versus I-off, and threshold voltage control and effective capacitance. We will go, as we go, I will explain the impact of all these things. And the process side, the key things are, most of you may be aware, litho, epi, and deposition techniques. Performance-wise, it's simple. The industry right now calls PPA. You add frequency and density. Yeah, so these are the key ideas which probably, I believe, at the end of this lecture, people should be able to take home. Can we go to the next slide, please? So the journey, it starts in 1947. Last year, I think we celebrated 75th year of the transistor. IEEE came out with a big celebration, and there are various societies which celebrated the 75 years of transistor. Now, how has that travel been? So from the point of a BJT, we went from the point contact transistor. We fabricated the NPNs and PNPs during the 1960s. They drove the market to some extent. Then 1960s see the birth of MOSFETs. The MOSFETs, if you can see, were the major driver up to 2000s, almost 40 years. We were very happy with the MOSFET planar technology. And then suddenly 2020, 2010 onwards, we moved to the FinFET nodes, gate-all-around nodes, because of the physical limits which we hit. So as you can see, suddenly from 40 years, a core technology driving for 40 years, and then the last 10 years or 20 years so, we have actually accelerated to 3 nanometers, from about 45 nanometers to 3 nanometers and down the line. The point being, the innovations and the changes are happening rapidly, and these are right now it was driven by computing, then by mobile, but now it's being driven by AI requirements. Can we go to the next slide, please? So let's start with the. I apologize for the quality of the slides. So let's start with the BJT transistor. All of us are familiar with NPN. What I would like the audience to focus on is, see, the initial technology when it was invented, it was a vertical transistor, meaning the the flow of current was from top to bottom. So what happens is, you can see the base width is 0.1 micron, but when this technology was invented, lithography had 1 micron only. So how did we get a base width of 0.1 micron? So what happened is, through diffusion and process temperature control, we were able to control the width of the base, that is the flow of the channel current. So that way, even though you had a 1 micron litho, you were able to do finer nodes. But it had one issue: the current had to travel from top to bottom. So with that came a lot of other challenges. So the main takeaway is, it was a vertical device, 3-terminal device, and there were some critical doping profiles which had to be clearly done for repeatability and yield to be obtained. And the most important thing was an NPN BJT was that it had to be isolated with a lot of techniques, which meant additional processes. Can we go to the next slide, please? So if you see, the main defining equation for a BJT is, collector current is defined by beta times the VB by VT. So what we can see is that we can see that there's a swing, the voltage swing which is achieved is, you have almost 0.8 volts, and there is a very good gain available at this particular device. And even to this day, the BJT is used in different forms because of the excellent gain which is given. But what also you can see is that base current is unavoidable. So there is always a base current which the BJT used to draw, and this did not allow it to scale it. So with this technology, you could not go for a million transistor complexity or things like that. So again, the industry came together and said that if we have to scale, we need to have a different device type. So that is how, again, the planar CMOS comes into effect. It had its other theoretical minority carrier device, early effect and things, but these were manageable. But the important factor was, for devices to scale, for more functionality to come in, the major factor of base current. Base current means a high quiescent current, and this will increase the power dissipation. So that was one of the main reasons why the BJT could not scale. But still, BJT is used in different forms in audio applications and RF applications, even to this day, in different variants such as silicon, germanium, and other devices. Can we move to the next slide, please? So with this background, 1959 industry came around and they thought, vertically, we can't have a vertical flow of current. Let's have a lateral flow of current. And then what are the processes which are required? What are the innovations which took place? We can see industry starts with a planar process, where the current flow is from source to drain in a planar way. Then you get a buried layer plus epi layer, basically to minimize the collector resistance. And then junction isolation, this becomes critical. Junction isolation and and with buried layer, what happens is, you could do multiple type of devices in the same substrate. So you had BCD, BiCMOS, so many things coming out of this particular two process innovations. So, but again, MOS had to scale, and for that, it needed to be low power and less leakage. So we will see what are the things which happened during this particular time. Can we go to the next slide, please? So if you see in terms of power, the speed, as we all know, bipolar is very fast, but the static current in every gate, that's huge. And the power also, again, with gate count increase, the power also scales. But even though there is no activity, the power is increasing. CMOS was a lifesaver for the computing industry at that point in time. You had major things of self-isolation, and the gate being a capacitor, you eventually removed the input current needed. So this was the biggest driver, and this allowed scaling also to be faster and lower. So one of the lesson, like whenever a transistor architecture changes, what happens is the scaling, how the scaling improves, and it is based on that factor alone. Sometimes you can get the fastest devices, but if it cannot scale, if the density is not increasable, then there is no point in it. There are multiple variants of FEMT and other compound semiconductor devices which are much faster than the CMOS logic, but they have not been able to scale. So that is the important lesson. Industry needs scaling at every crucial juncture. Can we go to the next slide, please? So now, how does the structure of a MOS basically actually comes into existence, and what are the knobs or the variables which the designer has so that they can achieve better performance? So you can see here, the gate is the most critical technology. Along with the gate, the width of the channel, that is the next. And for the designer, it is the W/L and the capacitance, oxide capacitance. These are the, along with mobility. Though mobility is a process level parameter, which is controlled at the foundry, whereas the W/L ratio is at the hands of the designer and the gate voltage. But you can see one important takeaway. This you would have already gone through your textbooks and your other detailed studies. But the square law is not exponential. If you could compare it with the BJT, the square law is not exponential. And again, in the current industry actual real-time requirement, the square law doesn't hold together for the upcoming architecture. But what we understand is the current dependency of the current on the capacitance, the ratio of the channel length, W/L ratio, and the VGS minus VTS, so threshold voltage. So these are the key takeaways. So as I said, please approach the device from its key components in terms of the gate oxide, how the electrostatics applies and currents modifies the current across the channel, and other technologies such as the threshold voltage and the capacitor, gate oxide capacitance, and so on and so forth. Can we move to the next slide, please? So, as all of you are aware, the power we know is dependent on the half CV square, where we focus on CV square. The capacitance is controlled. What the industry likes is, as and when you reduce the supply voltage, the power dissipation reduces and the speed also reduces. So the industry likes reduced power. But at the same time, we also have other costs to pay. As you reduce supply voltage, you are bringing in a whole lot of second order effects. Leakage is increased, static short channel current increase, drain DIBL effects, all these things prop up. But however, this again, with a complementary pair, there were some issues which were sorted out. But the innovation was the entire CMOS, planar CMOS technologies, even till date, worked on the scaling of the supply voltage and the channel length. Can we go to the next slide, please? So Dennard scaling is another important term. We all see how the scaling factor, but what actually is Dennard scaling is that there is a factor fixed, K factor is fixed, which is about 1.4 for each node. And then based on that, your channel length, supply voltage, doping concentration, gate capacitance, your drive currents, and gate delay, all these are scaled, meaning all these are reduced or increased or multiplied. So with what is the impact of the Dennard scaling? The idea is every time the transistor switches, the energy per switch is CV square. So you reduce the voltage swing, you reduce the capacitance, you get more power density per area. So Dennard scaling kept the planar CMOS alive for about 40 years. So for each technology, you have a different factor, but the main thing is that the physical parameters, basically the length and the electrical parameters, supply voltage, and the process parameters, the doping concentration, were all scaled by a factor, and this factor was dependent on each node. This kept the industry for close to 40 years. Can we go to the next slide, please? So when we say again, the constant field scaling stopped working. Why I say constant field scaling? When you apply a voltage, there's a field which is developed across the channel, but it doesn't always work when you keep on reducing the channel length and the drain voltage. What happens is, as I said earlier, the threshold voltage will not be able to follow your VDD, and VDD right now is stalled somewhere close to, I have said, is about 1 volt, but the latest technologies, it's somewhere around 0.6 volts or something like that. So we have seen devices being operated from 60 volts to 15 volts, 5 volts, 3.3, 1.2. Now we are somewhere around 0.6 volts. And it is going even more lower, but again, it has its own challenges. And the gate oxide, when we say the gate oxide, we can't keep reducing the gate oxide, because at about 1.2 nanometers, the silicon dioxide, which is actually sitting between the gate and the channel, is hardly about 5 atom layer thick. Okay, so it's like stacking 5 atomic layers, and that is your silicon dioxide. Now, if to achieve a thickness at that, it brings again with a whole lot of other physics related challenges. And frequency scaling also ended up to 3 to 4 gigahertz. We could go with the regular CMOS devices. Due to the gate capacitance existing, we were not able to go cut across beyond that. And obviously, short channel is like, it follows through with every scaling you do. Can we go to the next slide, please? So basically, what I said is, here it's a fight between the drain and the gate. Who fights and how does it control? So what we actually want is the VGS to control, modulate the current. But whereas you have the gate, because of the thickness being lowered and the channel being lowered, you are not able to get a good constant electrostatic field. At the same time, the drain is supposed to be, when you are operating at MOS transistor, the logic is that you saturate you operate it in a saturation region, but it's no more in a saturation region. Then there are other second order effects which come into play: the velocity saturation, hot carrier injection. These are all impacting the mobility part of it. So with all these are the common root causes being the gate. The gate is a separate technology on its own. And this, as you can see, I'll point out how the gate has driven the transistor to totally change its geometry. Can we go to the next slide, please? So one important thing what we have to understand during this particular lecture is the subthreshold swing, what we call, how fast actually the transistor can switch on and off with a margin. See, we have a KT by Q factor coming in with a log natural of 10, but how this is that the KT by Q factor is a physical factor which we can't play around with much. But the depletion oxide and oxide capacitance, that is something which the industry is struggling to control. But for right now, without, let me give a figure. You have consider around 60 millivolts to have a sort of comfortable on and off margin. Otherwise, you're going to have a lot of other tunneling effects and negative capacitance effects. So we need to have a comfortable swing of 60 millivolts. So that is a wall which, the planar technology was trying to, go around with. So keep this figure in mind. You can read up on this later. Can we go to the next slide, please? So as I mentioned, once you reduce, as you scale, once the gate oxide scales down to 5 atoms of silicon dioxide, there is a whole lot of tunneling happening. You can't actually control, your VGS does not proportionally control the current which is flowing through the channel. And apart from the leakage, there are many other effects, polygate depletion and nitride oxide, which, the process related things damage the structure of the transistor. Reliability figures came into the play. So now it had to be reworked in such a way that the gate had to be modified, and along with the gate, there were other process related changes which could actually improve the quality of the transistors. This happens again as we go down from, let's say, 90 nanometer, 65 nanometer, 40 nanometer. These are the challenges which actually comes into play. Can we go to the next slide, please? So what they did to control the channel, so they had a different variant of a silicon, strained silicon they called, from 90 nanometers, which actually played around with the strain basically the mechanical tensile strength, and also it had it could be fabricated with a sort of process in the current existing thing with a little amount of doping variation and things like that. So this sort of improved drive current improvement from just changing the variant of the silicon strain alone. Now this is what is done at the material fix, at the process level fix, and this is achieved by the lattice structure, the crystal structure. So to simply put, the channel recipe was slightly changed to give a performance improvement. And can we go to the next slide, please? Then the industry tried to work around the gate. So what happened is we had a poly gate which sort of controlled the electrostatics, and the even much older version was the oxide was the silicon dioxide or silicon nitrate. So what happens is, again we introduce a metal gate. So when you introduce a metal gate, what happens? The work function sort of remains changes, but still the second order effects due to that those tunnelings are by better control. And you have much better oxide coming in with a better dielectric with a K of 20 to 25. That brings down the leakage also. So without any change to the structure, purely by changing the recipe, the industry is able to get some improvements. But the important thing here is the way the gate gets built. That is the most important. From here, the fundamentals remain same, and the gate last integration, we call it gate last replacement gate, replacement metal gate, or whatever it is. That is the foundation for FinFET and gallium gate all around transistors. What happens is there's a dummy gate which is formed, and that is replaced at the last integration step with these sort of high K metal gates. So that is again a innovation which the industry has bought, and it is taking us from planar to FinFET and gate all around. Can we go to the next slide, please? So it's the same thing, whatever we have discussed. So the natural length, the channel length. So we talked about how the gate influences, but as the channel reduces, the drain's influence also increases. So no more your transistor is in saturation and it is not listening to you. It will have its own way of working around. And so now it means that you have reduced the channel length, you have reduced the gate also to extent, but how are you going to control the drain? Because you have reached the physical limit of the drain. Now you need something more. Let's forget the equations, but consider this. You have been reducing the channel length. Your drain is coming closer and closer to the source. Now the drain tends to play much bigger influence compared to your gate. Now, how do you overcome this? Now, this is where, can we go to the next slide, please? Now, this is where actually the channel which was there earlier in a planar form, the channel comes up. If you can see the FinFET, planar was like where the channel is like the gate is formed over the channel region, but you can see that the channel is slightly coming up on the FinFET, and the gate has three faces. The gate covers the vertical portion of it and the horizontal portion of it. So two verticals and one horizontal. So the gate has, you can call it that the channel has risen up, and there is a small fin which is being placed so that your depletion region is controlled. Now this is the FinFET. Now moving forward, FinFET has its own issues, and now the gate wraps around. That's what it's called, gate all around. The gate wraps around all the four faces of the channel. It's like basically stacks of sheet which are stacked 1, 2, 3, which I will show you. And around those stacks of sheets, you have the gate being wrapped all around the, so which gives you a much more larger surface area and larger current, but at a lower channel length. Can we go to the next slide, please? So during the FinFET region, when the channel came up, you could see the width per unit area for that particular planar length, the width increased, and there was twice in impact, and the sub-threshold swing was around 65 to millivolts, and the operating voltage was 0.7 to 0.8 volts. From a planar process, the performance increased up to almost 37%. So the electrical impact, if you see, so with compared to a planar process, what you're getting is you're getting much more in a smaller area, more performance in a smaller area. That is where FinFET actually contributed to enabling this. And this technology you can see almost in all the mobile phones. This technology drove all the mobile phone architectures even till date. Can we go to the next slide, please? So now, till now, the industry was working planar, and what it had to do to actually make a fin was you had to do fin patterning, you have to do a fin reveal, and you had to do a dummy gate. So many process structures, process steps had to be added in the transistor fabrication. Now, this required lithography steps which were totally different from the legacy lithography lithography principles, and you also had to deposit and etch vertical structures. So this created a huge amount of complexity for fabrication, and this meant that only 1 or 2 foundries could do these. So the FinFET now is being patented by probably Intel, TSMC, and a couple of foundries, major 4 to 5 foundries, which hold the key patents for including the process and the device architectures. Can we go to the next slide, please? So again, yes, the fins, what happens? Can you keep on increasing the channel? Because what happens is if you keep increasing the height of the channels, your fins become mechanically fragile. So that becomes a problem, and you are sort of faced with certain other ratios. The aspect ratios sort of make sure that your process related steps are you cannot meet the yield. Actually, FinFET yield itself is really low compared to your CMOS nodes. So the planar nodes. So the yield problems come up, and parasitic capacitance dominates. So what you are faced with the 2D capacitance, now you are looking at a 3D capacitance, and that has to be modeled, characterized, and has to be brought into your device model. So again, that is another part of it. And the fifth point is where even now the designers struggle is that electrostatics fall short below about the gate length of 15 nanometer. What we mean is that, as I mentioned very earlier, your square law doesn't hold anymore. So now concepts like quantum confinement comes up. VTH is not able to behave properly, and what you're trying to bias the device, you can end up somewhere else. But of course, it is not a big gray zone. The EDA tools have evolved, and empirical data is available to the the circuit designers, and the logic designers. The designers make use of complicated models to fit the mean curve across, so that the overall functionality is met. So what they did was, yes, with all those things, still they want to improve the PPA. They thought, okay, let's not go vertical alone. We will wrap the gate around the channel. So it's like wrapping you consider it like a pillow cover. So you have a channel and you have a pillow cover. So your gate is like a pillow cover. So they wrap their gate all around the channel. That gives a whole lot of different physical and electrostatic improvements for the transistor structure. Can we go to the next slide, please? And this actually, before we go, this starts from 3 nanometers onwards, and again, there is a whole lot of industry, terminologies which say 12 nanometers, 10 and 7 nanometer, 5 nanometer, 3 nanometers. Beyond, let's say about 28 nanometer or 22, I think beyond 14 nanometer, the gate length sort of remains constant. It's about 12 nanometer. The marketing terminology does not reflect the gate length. What is reflected is the poly pitch or the metal pitch. So when they say 1.8 angstrom or something like that, it doesn't mean that the channel is 1.8 angstrom. The channel may still be about 12 nanometer, but the poly pitch or the gate pitch might be very closer. So gate all again, from here onwards, what is again another phenomena is most of the research in the planar and the FinFET domain was made open source and was available to almost everybody. but the research which is happening with gate-all-around are restricted to very few companies, and because this gives a technology edge for the next many years to come. So these are all being done in proprietary research labs, and everywhere around these sort of structures are being fabricated and seen and developed and characterized. So what happened, Samsung recently, about 2 years back, they released the gate-all-around. That was followed by Intel, TSMC with, they call it N2 node with the nano sheets. I think N2 or N3 is already in production with the recent, I think, iPhone are all with NVIDIA versus, I'm not sure about it. But these are already entering production. And now, along with Moore's law, they're also looking at more and more technologies to accommodate the thing. But that is not the scope of work for this particular presentation. Can we go to the next slide, please? Kishore, can we go to the next slide? Yeah. So again, when we go gate-all-around, you do atomic level manufacturing processes, which again introduce a lot of need for fabrication equipment. So a totally different set of fabrication equipment and different types of process steps, which are not existing as of now in most of the commercial fabs across the globe, except 1 or 2 fabs have this. The super lattice epitaxy patterning is anyway already commercialized. But the epitaxy for the gate-all-around transistors and the gate stack fill, these are atomic layer deposition. These are all techniques which are being done at very, very highly precision control using equipment. Can we go to the next slide, please? Okay, process being one side. So what is the actual win from the gate-all-around? From the gate-all-around, you are able to sustain the subthreshold swing. You have reduced the transistor, but you also increase the subthreshold swing. The VTH is not dropping, so that the leakage is still remaining. But you can also, the VDD is still coming down, which means that you are going to scale further. And you can add more complexity. So you can jump from, 1 or 2 order of jumps from, if it was 1 billion gate, you can go to close to, 1 or 2 orders very easily with this sort of, and it's the same thing. You can understand that we are dealing with the same electrical parameters: threshold voltage, gate length, drain-induced barrier, subthreshold impact, capacitance, and drive current. These are the main key electrical parameters which will help you to analyze any transistor architecture if you, at least in the MOS region. Can we go to the next slide, please? So when you see a comparison of planar versus FinFET versus gate-all-around, so you could see there was only one gate. FinFET has gate 3 surfaces. Gate-all-around has 4 surfaces. And the channel is thick, whereas the FinFET and the gate-all-around channels are sheets. Basically, these are sheets which are stacked, basically. And your effective width, W by L, your width is actually increases in FinFET and gate-all-around for the same area. But again, we are able to maintain a subthreshold swing of 60 millivolts, above 60 millivolts. And there are other things which are there, but mostly the threshold voltage becomes a work function of metal. Basically, the high K dielectrics and the metal, it's a function of both these things. So the metal gates coupled with the high K dielectrics give a better work function, wherein your electrostatics are totally different compared to your square law. And there are other processes which are introduced which may not be relevant right now. For it'll require a deep dive, but to overall get a broad understanding, you can see that the gate surface, the channel body, and effective width, these geometrical parameters impact the electrical parameters of your subthreshold swing, drain-induced barrier, and threshold voltage. Can we go to the next slide, please? So if you see, again, I'm repeating myself, the electrostatics. So if you see the electrostatics, you have subthreshold swing and the drain. These are one of the key figure of merits. And you at gate-all-around at 2 nanometer, you are still somewhere for the subthreshold swing is somewhere very close to your FinFET process. being very close to the fin-fed process, but still you are able to reduce the drain-induced barrier leakage. So that is something which is very good, and that is being because of this you are completely different form of very highly stacked applications for the AI models and accelerators are coming up. Can we go to the next slide, please? I think I have another 5 or 6 slides. Do I have enough time, Kishore?
Yes, we have a hot stop at 3:30.
We are having one
I have
minute,
4 minutes.
one minute, Karthik. We have MCQ to be done. We should have what. So if we can close it quickly, that will be good. We don't have time. Actually, by 3:50 was the time. Okay.
Yeah. So I think we will stop here. So to get an overall idea, what you can see is that with the change in the transistors, the gate length is sort of, as we go down the node names, the gate length is still around 12 nanometer. And then when you go to the supply voltage, it is somewhere hitting at around 0.6 volts. So with this, I think I'll end my presentation and we'll open for any questions.
Okay, before that, we'll have a quiz, sir, that has been shared by you. Request Ari to post the quiz link in the chat box. I request the participants to join the Slido quiz. Hope you are familiar with the process. Past 2 days, you have been participating in the quiz. It is a time-based quiz. We'll have 20 seconds for each question. Total, we'll having 5 questions. I request the participants to join up to 700. We have the limit and we can start the quiz. Pati sir, you are on unmute. Okay. We'll wait till it reaches 700. Okay. First question. This is the lecture given by Mr. Saravanan sir. Okay. Mixed answers. We'll see the right answer. Okay. 47 of you has got the right answer. Second question. Okay, let's see the right answer. Third question. Okay. Fourth question. Okay, we have a mixed answers here. Okay. The final question after this, we'll have a leaderboard. Okay. Thank you. We'll reveal the leaderboard. Okay, these are the top 5 participants who answered all 5 questions in the 39 second is the top. Anirudh is the top person who received the award. Thank you. Before closing the session, I will have an announcement. We'll have a post-assessment quiz which will be shared in the WhatsApp group. Hari, can you paste the WhatsApp group link? Hari, can you paste the WhatsApp group link?
Yes, sir. Yes, sir.
Okay. The WhatsApp group will be active. We'll be pasting the post session quiz in the WhatsApp group. We'll be opening, it is a Google form. We'll be opening the Google form in 2 time slots, morning half an hour 10 to 10:30 and afternoon 2 to 2:30. The both those who have missed the morning slot can attend the afternoon slot. Any one slot has to be attended. We are giving 2 time slot for the student convenience. The participants only have to attend any one of the time slot.
Faculty people also can attend. Correct, Naresh?
Yes, sir. Yes, sir. All the participants, based on the evaluation, we will be providing the certificates. Okay. Now I request Mr. Pati Lakshminarayan sir to give the vote of thanks.
Thank you, everyone. On behalf of PALS organization, I express our heartfelt gratitude to all the speakers, especially Dr. Saravanan and Dr. Karthik today. And then it was a very nice gesture from them in spite of lot of work in their organization. They have taken some time to come and then speak about the current technology in semiconductor, VLSI design and transistors, etc. So really, PALS organization is thankful to them. We really appreciate the effort from both of them. Thank you very much, sirs. Then I also thank the faculty members and then college students who joined here for the last 3 days, not only today. I also thank the PMO organization of PMO team of PALS who had an extraordinarily good job in conducting this session. These sessions are not it was very overwhelmingly attended. 5,000 plus people attended for every session, and then around 2,500 people took the Slidos. As a saying goes, learning is a treasure that will follow its owner everywhere. So we leave this session with the new knowledge, fresh ideas, and renewed motivation. I thank once again all the people who participated. Over to you, Kishore.
Thank you for the sir. Thank you. We can close the session, sir.
Because of the time constraint, we could not have questions. Sorry about it, because our students are having hard stop and then they have to leave the campus for catching up to buses, etc. Thanks.
Thank you, sir.
Yeah, thank you all.
Thank
Thank
you.
you, sir. Hari, stop the recording.